Okay, for this one, I know it's already 2:30. I don't think I'll get this done, but whatever I don't get done, Everett will finish with you on Thursday. He will be my sub fourth period on Thursday. So, and he knows a little bit about calculus, so he can pick up where we left off. Today, we're going to talk about two important calculus theorems. Rolle's theorem, named after a guy named Rolle. And we're going to talk about the mean value theorem. And like a lot of the other things I've done in the past, I'm going to try to keep it simple and explain it in a way that makes sense. Okay. So we're going to talk about Rolle's theorem, we're going to talk about the mean value theorem, and you should be able to count to 10 in German. Yes? I can. Eins, zwei, drei, vier, fünf, sechs, sieben, acht, neun, 10.
We won't have to be doing calculus in German.
I'm sorry, what?
We won't have to be doing calculus in German.
You never know.
Oh.
Oh, okay.
Okay.
You're gonna do calculus in German?
Did I take calculus in German?
Equal words.
That's true. Okay, so, strangely enough, and hopefully you can appreciate the irony of this, this guy named Michel Rolle came up with a theorem involving hills and valleys. And an easy way to understand rolls is to remember what it means to roll a ball up a hill or roll a ball down into a valley. Okay. So, we start with this idea. We have a function, and it's continuous, and it's differentiable. Okay. Now, what does that mean? Well, you know what continuous means. What it means about being differentiable is that there's no points on the graph where you cannot take the derivative. I know that's a double negative, but roll with it. There's no cusps. There's no jumps, because that would be discontinuous. There's no weirdness. It's just a function. But part 3 is key for Rolle's theorem. And that is you're starting and ending at the same value. Okay? Now, whether that's the x-axis, whether it's y equals 7, it doesn't matter. But you start and stop at the same time. So Rolle came up with this idea that if I start at one point, I travel along the function and come back to the same point, at some time along that path, one of two things has to happen. I either hit the top of a hill or I hit the bottom of a valley. Okay? Does that make sense? Okay. Think about it this way. I'll draw you a picture. I start with level ground. I'm going to start here. I'm going to end here. I have to start and stop at the same y value. And then I put a function in here. This one happens to be a hill. Can I get from point A to point B without hitting the top of the hill? No. I got to go up the hill, I hit the top, and then I got to come back down. And the key in that is that you're starting and stopping at the same value. Now, Rolle said there is a number, but there can be multiple numbers, but there's got to be at least one. I think it's easiest to remember if you're rolling a ball up a hill, but you could also think about rolling it down into a valley. Okay, if this is my valley, I can't go down from A and get back up to B without hitting the bottom of the valley. That maximum or that minimum, because we already know that terminology, is they commonly use the letter C to represent that location. Okay, so this is at the x value of C. This is at the x value of C. There can be multiple C's, but there's got to be at least one. Does that make sense? Yeah. Okay, and you remember Rolle's theorem by rolling a ball up a hill and then back down the hill. If you do that, you got to hit the top of the hill at some point in time. Good so far. How do you apply that? Well, you get rid of this mess on the screen first. And you start with a nice parabola. Okay. Gabriella, what can you tell me about that parabola? Oh, yeah. Anything else? I was looking for something even simpler. Which means? Yeah, it opens up. Good. So we'll get a minimum here, right? Okay. And there's a reason why I started with a parabola, because it's fairly easy to see. we want to find those c values on the parabola, so you know by now that it's a parabola. I'm going to get one c value. And Rolle's theorem says that that has to happen. Now, what we're wondering, though, is does it happen on the interval from 1 to 2? In other words, is the vertex of that parabola between 1 and 2? And we can check that in a second. Whoops, skip that pretty quick. All right, if I go back to this screen, I have 3 conditions I need to meet in order for Rolle's theorem to apply. Is that function continuous? Yes? How do you know? Is that right? How do you know that?
Because like there's no, like it's not divided.
How do you know that?
X isn't in the
How do you know that? You see where I'm going with this? Yeah. How do I know that that function is continuous? Jessica? Polynomial. Okay. Which everything you said was true for a polynomial. I was just looking for that. Part B, it's got to be differentiable. Is there any point on that graph, from what we know, where you can't take the derivative? No. Okay? So we move on. The third part is the important part. Does it start and stop at the same value? So I need f of 1 and I need f of 2.
How did we know it was differentiable?
Because it's a polynomial.
Oh, same thing.
When in doubt, yes, it's a polynomial. Leona, what's f of 1? Say again, please, I'm sorry. 0, yes? Yeah, okay, good. What's f of 2? 0. Oh yeah, we're doing some Rolle's theorem here. I picked a particular example where those values are equal to 0. That doesn't happen. Oh, that was weird. That doesn't have to be the case. There we go. Now I lost all my work. Great. It doesn't have to be equal to 0. They just have to be the same value. You could have gotten 7 and 7. You could have gotten 12 and 12, as long as we're starting and stopping at the same y value. Okay, so we know that f of 1 equals 0, f of 2 equals 0, and therefore we can apply Rolle's theorem because we've satisfied all 3 conditions. It's differentiable, it's continuous, and we start and stop at the same value. But now we want to find where those points are. We did those points in the last slideshow. Take the derivative, set it equal to 0. Done. And so what does that mean? That means that at x equals 3/2, that parabola either has a valley or a peak. And because we're dealing with something simple like a parabola, we know that it's a valley, based on what Gabriella told us earlier, that the parabola opens up, and therefore it's got to have a vertex, which is a minimum.
So whatever the value, the first value is 0, it could be 7.
Could be
You
any.
would just plug into f of x.
Yep.
Like like if it was 7, it'd be 7 equals 2 x.
Yeah. If I change my interval, for instance,
Yeah.
into, like, let's say, -2 and 5. Okay, just for giggles, let's see what happens here. Again, I'm winging this. F of -2 and f of 5. F of -2 is 4 minus, no, plus 6 is 11 is 13. And f of 5 is 25 minus 15 is 10. Ooh, I was close. Okay, Rolle's theorem doesn't apply. We're starting here and ending here. They have to be at the same time.
Can you go to the hallway for minutes?
Sure. All right, any questions? It's important moving forward that you understand Rolle's theorem, because if you understand Rolle's theorem, the mean value theorem is much easier to comprehend, and we'll spend a majority of our time with the mean value theorem. Okay, any problems? Beautiful. Okay. So then we do the mean value theorem. Question?
Sorry, if you plugged in your interval and like you got 7 and 7 says you're 0, would you plug 7 in for f prime x instead of 0?
No. I erased it, but you're not plugging anything into f prime. You're solving for where f prime is equal to 0. You're solving for a max or a min.
No, that's like what I meant. Like since our interval both equals 0,
Mm-hmm.
and then we plugged in 0, like if the interval both equals 7, would you plug in 7?
No.
Oh, just always 0.
Always 0.
Oh, I thought you said the other opposite.
Did I not answer the question you asked?
Yeah, I thought, because you were saying that like, if f of 2 and f of 1 were equal to 7,
Mm-hmm.
then you would make the derivative of that thing equal to 7. No,
Still equals
opposite.
0. Yeah, that second point is always 0 because that's what's going to tell us where the max or min are, where the tangent line is horizontal. One of the things that pops up a lot in calculus is that if a theorem has its own name, it all of a sudden becomes important. Some of them more important than others. You will hear about mean value theorem a ton of times. Rolle's theorem will be mentioned, but not nearly as important as mean value theorem. And the only difference between mean value theorem and Rolle's theorem is you spin the circle. Sorry, you spin the graph. Okay, what do I mean by that? If I take my Rolle's theorem, where I had something like this, and there's my C value, and I start at A, and I start at B, and they have to be the same value. So f prime of C would be equal to 0. F of A equals f of B. If I take that whole picture and I spin it, which I don't think I can necessarily do here, I'm not even going to try, then it becomes the mean value theorem. And I have a picture to show you in a second. Okay? So what does that mean? So we get this, here's the mean value theorem, and it follows the same rules that we had with Rolle's theorem, except for the fact that you'll notice there's no part 3. We don't need to start and stop at the same point. It has to be continuous, and it has to be differentiable. That's it. And then, if that's true, we get this stuff on the bottom, which we'll address in a second. Okay. Doesn't have to start and stop at the same point. What this stuff at the bottom is, well, you tell me. The right side of this equation should look familiar. What is it? Say again?
Slope.
It's a slope of what? Secant line, correct. What's the left-hand side of that equation? Somebody said it. Maybe not. What's the left-hand side of that equation? Slope of the tangent line, correct. Okay. So the mean value theorem says the following. Wait, hold on, I'm jumping the gun here. Here's a picture. Here's my function in blue. So you can see where this is Rolle's theorem that I just turned it a little bit. This purple line or brown line is no longer horizontal, it's askew. And I can calculate the slope of that purple line by doing this. Remember, f of whatever and f of a and f of b are y values. So that's y2 minus y1 over x2 minus x1. What the mean value theorem says in simplistic terms is that the slope of the secant line, there has to be some spot on the curve where the slope of the tangent line matches. Okay, so you think about if I take this secant or this tangent line and I start moving along the curve, at some point I've got to get to a point where it has the same slope as the secant line. What does that mean? That means that one of the buzz phrases that we use with mean value theorem is the following. Come on, Reedy. There we go. Slope from calculus equals the slope from algebra. Over and over and over again. And I don't know how you want to put this together. Like one way is you could look at this also applying to Rolle's theorem, except when you calculate the slope of the starting point, you're going to get 0 every time. And when you calculate the slope from calculus, you're going to get 0 every time. The mean value theorem just spins it. Excuse me. Questions so far? It will make more sense when I show you an example. So let's do that. If this were the problem for Rolle's theorem, we'd plug 2 into the function, we'd plug 7 into the function, and if they were equal, we'd be good to go. Mean value theorem, like I said, doesn't care if they're equal. Okay. Is the function continuous? Yes or no? Yes. How do you know? Polynomial, good. Is it differentiable? Yes. How do you know? Beautiful. Okay, we're in business. So now we're just going to do what we know. And that is we're going to find the slope of the secant line, which is the slope from algebra, and we're going to find the slope of the tangent line. Okay? So let's find the slope of the secant line. Slope of the secant line, I need f of 2 and I need f of 7. Go ahead, little help, please. You guys could get out your calculators and help me a little bit. Suppose you got some answers for me?
Yeah.
I can't hear you.
12. The f of 2 is 12.
Can somebody confirm?
Yes.
And f of 7?
87.
87. Again, if this was a Rolle's theorem problem, we're done. We can't go any further. It's not Rolle's, it's MVT. So the slope from calculus would be 87 minus 12 over 7 minus 2, which is 75 over 5, which is 15? 15. Okay. Now what does that mean? That means I've got this parabola that faces up. And I took a point here somewhere, and I took a point over here somewhere, and I calculated, I missed. I calculated the slope of that secant line and got 15. What the mean value theorem says then is somewhere over here, there's got to be a tangent line with a slope of 15. I'm looking for where that point happens. That's C term, also known as a mean value theorem value. To do that, I take the derivative and set it equal to 15. So I'm going to stop there with this guy before I solve it. That is the true definition of the mean value theorem. The left-hand side of that function is the slope from algebra that we calculated in blue. I should have flipped them the other way. The right-hand side is the derivative from calculus. The mean value theorem says those two things have to be equal. I set them equal, and then I solved. So I think x is equal to 9/2.
Yeah.
Okay, good. Last question here. Is 9/2 in the interval? Yeah, and you need to check that too. Because you can get C terms that are outside the interval, and all we care about in this particular problem is this interval. Say again, I'm sorry.
What happens if you guys turn out something? Doesn't that mean you
There does, and there almost always is. It is possible you will see a few weird instances where you might get multiple C terms, but they're outside the interval. You might get some weird situations where maybe one of the C terms is one of the endpoints, which doesn't work, but for the most part, I want to say you almost always get one answer, but sometimes you'll get, multiple answers. Because if you think about that, if it was a cubic I started with, I would be setting a quadratic equal to some number, and that would give me the two answers.
Oh.
And then you got to check to see if they're in the interval.
So like, what is the 9/2?
That's this point. That's the point on the curve where the slope of the tangent line matches the slope of the secant line. The slope from algebra matches the slope from calculus.
Wait, so the point on the line where the slope of the tangent equals the slope of the secant?
Correct.
Wait, why don't I get the point on algebra equals it? Like, why is it?
Well, this is just an algebra calculation. y2 minus y1 over x2 minus
That's the
x1.
calc.
And then the green is the calc thing. Any other questions? Let me clear my mess out of here. Clean. Okay. And we'll do this one in blue. Same problem, but something weird happens in this problem. So let's go back to the definition of the mean value theorem. By the way, bust out Desmos or your graphing calculator and graph that function, please. 5 minus parentheses 4 divided by x. In order for the mean value theorem to work, we have to meet two conditions. You'll have to trust me on this one. That is a differentiable function. Is it continuous?
No.
What did you say? Let me ask my question again. Is the function continuous?
In that domain, yeah.
Ah,
Yeah, it's not.
but you didn't answer my question.
Well,
No.
not the
No,
overall.
the function is not continuous. However, as you said, Falcon,
In that domain, yeah.
in the interval from 1 to 4, the function is continuous. I think I have a picture on here, don't I?
Yeah.
Yeah, there we go. Okay. That would have been easier if I just clicked on the picture. We've got an asymptote at 0. But 0 is not part of our interval, so we're still good to go according to the mean value theorem. It's differentiable and it's continuous. So here's my slope from algebra. And then I have to do my slope from calculus. Slope from algebra, if it's 4, f of 4 is 4 minus f of 1 is 1 over 4. Oh, well, that's 1. Okay. That seems to, did I do my math right? Why does that seem so pretty? Okay, whatever. Okay, good. Self-doubt. Let's see, that would be, this is 5 minus 4x to the negative 1, so the derivative would be 4x to the negative 2, which would be 4 over x squared. Slope from calculus equals slope from algebra. Therefore, x is equal to plus or minus 2. What's wrong with that answer? Nathan?
The negative 2.
Negative 2 doesn't work. So we're going to get rid of that, and we're just going to say x is equal to 2. We throw out the negative answer because it's not in our original domain of the problem. Okay. I think the biggest problem is going to be remembering the differences between Rolle's and mean value theorem. For the most part, they're an identical theorem. It's just mean value theorem is more versatile because you don't have to start and stop at the same value. This, by the way, is a bridge in, I believe it's in China, and for some reason they felt the need to put the mean value theorem on the front of a bridge.
You're on the way to a test and you pass under that bridge.
What's that?
You're like on the way to like a math test and you pass under that bridge.
Or if you could see that outside your classroom window. That would be, yeah, wouldn't that be nice?
Did they like close the blinds?
Maybe this is a major university and they just try to help their students by,
That's something like they're always presenting just that.
yeah. Of all the things you could put on a bridge, they chose the mean value theorem.
Well, I mean, if you put the periodic table on there,
You wouldn't be able to read it. Yeah, that's pretty legible, especially from like a 5th-story window.
And the color coordination is good.
Yeah, it's good. Yeah, matches the part of the buses.